Okay. Now that we got this. Okay, here's the problem. Use the Biot-Savart law to find the magnitude of the magnetic field at point P, that is a distance d away from an infinitely long wire carrying a current I. Express your answer in terms of the variables given and any physical constants. Okay, so I'm just going to draw the picture. The picture is the most important thing. This is a wire. It goes over here to negative infinity, and it goes over here to positive infinity. Super long wire. It also has a current, I. And it is going from left to right. And we are asked to find a distance d from the bottom of the wire. This is d. There is a point P. Magnetic field is normally considered as the letter B. What does the magnetic field equal? Express your answer in terms of the variables given and any physical constants. So that's it. That's the full picture. And they ask you to use the Biot-Savart. Is it Savart or T? Biot-Savart. My bad, Mr. Savart. T. What is that? I'm gonna straight up just Google it right now. And it looks like, ooh, pretty complicated. Pretty interesting kind of law. Let's take a look at it. So we got B is equal to mu subscript 0I over 4 pi. Mu subscript 0I over 4 pi. Those are some constants. Integral. Damn, integrals are scary. And inside the integral, we got a fraction that looks even scarier. ds vector cross r vector. ds cross r. And normally this r has a little hat. Yeah, in this equation it has a hat, and this is r squared. Biot-Savart law. So when I solve this problem, the first thing I want to figure out is what equation am I using. This is the equation. Interestingly enough, this equation solves for the magnetic field because on this side of the equation, we have a B. On that side of the equation, we have a bunch of shit. If we plug that shit in here, we get a B. Cool. The question is, how do we plug stuff from our picture here, the infinitely long wire, into here? Well, you gotta know what you're talking about. So automatically, I can see current is over here. So that is good. Boom. This is a constant, 4 is a constant, pi is a constant. So all of these things we have. I'm just circling what we have. This r squared normally is the distance. If you read about the electric field and magnetic field, you see that this guy here normally is r. Except in this case, we call it d, and here they square it. So we take d, boom, plug it in there and square it. The question is, what is this? So I'm gonna circle this because we also know it. We don't know what this is. Okay. This is a cross product. We have A cross B. Both of these are vectors. This ds vector is the direction of the wire, specifically the direction where the current is going. So over here, I can draw a tiny ds with a vector. Why is it a tiny ds? Because we cut the wire in a small segment, dl, for example, super small segment of this infinitely long wire. We can change the L to an S if we want. It's just whatever variable. Most of the time you see ds here, and it is pointing in the same direction that the current is pointing. If I flip the current, this vector will flip directions as well. So that is the first vector. This r, notice it is the same r as this, except it has a hat. That is the direction from this towards your point where you're trying to calculate the magnetic field. And it has a hat on top of it because the length of this r is equal to 1. So this is called a unit vector. The only important information about this r is that it is pointing in the direction of the separation vector here. Cool. Now that we know that, we can do ds cross r hat. Cross product. I have defined one vector, the first one. You can consider it vector A. And I've defined the second vector, r hat. You can consider that vector B. Cross products obey the right-hand rule. This is my left hand. This is my right hand. The thumb normally points in the direction of this vector. Your pointer finger normally points in the direction of this vector. And if you make this kind of square-looking thing like this finger points in the direction of the result of this cross product. So let's say this is C. Cross product spits out a vector. Check out my vector video for that. And if I do this, I can find the direction of this. So I have ds, my thumb. R is pointing down like this. So if I hold it like this, with respect to the page, the result C will be pointing into the page. That is telling you that the magnetic field at this point is pointing into the page, which normally is defined by this X. Also, take a look at some vector video. If it is going into the page, it's defined by an X. If it's going out of the page, it's defined by a dot. Out, in. So that's important because the B is a vector quantity. That's not too important because this problem is actually asking us for the magnitude. So anyway, we don't need that. Another thing you can use here, if you want to find the length of this vector, the magnitude of this vector, is you have this kind of identity times, is it sine? I think it's sine theta. This has a length. The length is super small segment of the wire. This has a length. Its length is 1 because of the hat. That's how we've defined it. Length times sine of theta. Theta is an angle. Sine of theta is some unitless number between -1 and 1. This times this gives you a length, and that length is the exact length of C, the result. So how we can do this is sine of theta is 90 degrees. So sine of theta goes like this. I think it starts here. This is 0. This here is pi, which is 180. So right in the middle is pi over 2, which is 90 degrees. So this is 1. So this sine of theta just equals 1. So this is equal to ds times r. R hat is 1, so this is just equal to ds. What is ds? We don't know. It's a length. I'm just leaving it as a symbol. So this entire thing breaks down to this. Maybe that was a little crazy. Take a look at it. I might erase it here so I can save some room and do some calculations. But what that means is we can simplify this equation now. We have B equals, I'm going to rewrite everything. Mu naught is a constant. We are normally given this. I is not a constant, but it is given to us here as a letter. So I'm just going to put the letter there. If they give you a number, let's say 1 amp, 2 amps, 1 milliamp, plug that in there and convert the units. 4 pi, we have integral. We keep the integral. I just calculated that ds cross r hat is equal to exactly ds. On the bottom here, we have r squared, which we said is d, so I'm going to just do d squared. What do we do from here? Well, we have to integrate, which is actually not the best. And another thing is the integration bounds here are from -infinity to infinity. Okay, but what we can say is d is a constant, right? So we can pull d out because d is not changing, it's just there. If we were moving this point back and forth, then this would be a variable and we can't pull it out of the integral. But in this case, we can pull it out of the integral, which simplifies this a little bit more. Here we have I, here we have 4 pi d squared. Here we have the integral, which is from -infinity to infinity, if I'm not mistaken. Technically, what you're integrating over is ds, the small element of the wire. The reason you do this is because this small element of wire has current running through it. this small element is creating a magnetic field here. So what we have to do with the Biot-Savart law is calculate the magnetic field. All of this is basically doing that for each of these small things, and that's what an integral does. It breaks up this wire into small segments. I calculate the contribution of the magnetic field from this singular segment. I add this, I add this, I add this. So that's why the bounds here are from negative infinity, which is where the wire starts, to positive infinity, which is where the wire ends. So you're adding up all of those contributions of the current at this point, and you're calculating the magnitude of the field. But we saw that d is a constant, we can pull it out, so that just leaves ds. An integral is a little complicated. You might have to know how to do this, you might not. But basically, integral of this is literally just diverges. Shit. That's not good. Are we screwed? Chad, are we screwed? So my mistake was that, you know how I told you guys about this summation of the contribution of this piece of wire, ds, to the magnetic field here? Well, this r here is not the same as this r, which we said was d. It is actually from here to the point here, and this does not equal d. What it actually equals is, well, if we take this from here to here, and we call this x, or we call this s, or we call this l, whatever we call this part of the triangle, you see a triangle forming over here, is a specific distance from the point here, which is right above the point where we're looking for the magnetic field for. So I want to find this over here, and this actually, you could use some Pythagoras. So this is the hypotenuse, which is c, which equals square root of the legs. Let's call one of them x squared, and the other one is d squared. Okay. So this was the mistake. This thing is actually what's supposed to be plugged into here, r. So I'm gonna erase this. Erase this, and go back a couple steps to the integral. If you're a little confused with what I'm doing here, I'm basically just rewriting this because I made a small mistake with what r was, right? As you move along the wire, the distance from this point decreases or increases. And if we go right here, and we're located right here, the distance from the wire to the point is d. But if we move along, the distance now is not d, it changes. So I made a small mistake earlier. I wasn't considering the entire picture. This is why it's important to draw a picture. So anyway, we have the r, which is down here at the bottom. Actually, am I doing this correctly? So we have ds, right? The cross product thing that I did with here still, I think, applies. So we have this here. Inside here, we have x squared plus d squared equals, inside here is a square root, and this whole thing is squared, right? Because this is what r is. X now is the variable related to this s. It's going along the same axis, so if we want to simplify this, make it look like an integral, I can replace that s with an x. Remember that this d is a constant. This d is not shrinking, but this x, it is shrinking and growing. It's sweeping across from negative infinity to positive infinity. That's why the integral is with respect to x, and x here is the variable. So if we simplify this, this square applies to the square root, and it removes the square root, and the square also disappears. Now we have this integral here, x squared plus d squared dx. What we could do here is u substitution. U is equal to x squared plus d squared. That means du is equal to 2x. That means u over here, if we plug in negative infinity here, squares it, becomes positive infinity. If we put infinity there, it squares it, turns positive infinity too. It doesn't make sense here. It does not make sense. I'm a bit lost. So I'm gonna erase all this, erase this, erase this. Just give myself some room to work here. Okay, we have b is equal to mu naught I 4 pi integral. Here we have infinity, here we have negative infinity. Here we have ds cross r hat. Here we have square root x squared plus d squared squared. Can we simplify this? But also take a look at this. ds and r, I said, like let's say we continue the wire here and we're looking at this little segment ds. R is now pointing in this direction, r hat, because r hat is always pointing towards the direction where you want to locate the magnetic field. So now ds is pointing this way, r hat is pointing this way, and this is theta. So the equation here changes a little bit. Okay, so we're going to actually use this because I noticed that something is happening here. As we sweep across this integral, that's what the integral is doing. It's adding up all these little contributions of the magnetic field created by the current along this wire. But, you know, r, the distance here that we said, this square root x squared plus d squared, this is a distance, this is r. This changes as x sweeps from negative infinity to positive infinity. But so does this theta. This theta shrinks and grows. As you go further this way, the theta shrinks. As you go here, the theta kind of increases until you get to this point. The theta is maximum 90 degrees. Then it goes here, and does the theta still continue increasing? I guess it does, right? Anywho, I'm going to keep that in mind and modify the equation over here. So we have mu naught I. I'm just recopying the same shit here, and I'm kind of thinking on my feet to see what's happening. So we have negative infinity, infinity. This ds r is equal to ds times r times sine of theta. Don't worry about that. Here we have x squared plus d squared. Man, we got so many variables now, bro. We got s, r, theta, x, d. Like, what is happening here? Okay, let's keep going. Mu naught I. We have 4 pi. We got the same integral, infinity minus infinity. Let's see here. So this r hat has a magnitude of 1. We don't need to worry about that. This ds stays. Actually, we could change this ds to a dx because we're talking about the x-axis here. We just use the variable ds because this is a general equation and it's not always applied to a wire on the x-axis. So ds is general. It could be a 3-dimensional variable or 2-dimensional, whatever. In this case, it's actually 2. That's why we're including this little sine theta here. So let's see what we can do. Here we go. How do we replace this sine theta? We'll take a look at this. This is theta, right? We have a triangle that is comprised of ds or dx or whatever. Over here is r, and over here is d, right? If I consider this entire thing, boom, boom, boom. The angle here, theta, is this. So how can we relate this theta to variables d, r, and for example, this would be a big X. The way we can do that is by using SOHCAHTOA. So sine is sine of theta equals adjacent over hypotenuse. Adjacent over hypotenuse. No, opposite over hypotenuse. SOHCAHTOA. Opposite over hypotenuse. The opposite side of this is d. The hypotenuse of this is r, which we said was square root x squared plus d squared, right? It's right here, r. I'm just replacing it. Now we can take this whole thing, plug it into this, and see if it kind of simplifies stuff. So at the top we have dx. We also have a d, which is coming from here. At the bottom we have x squared plus d squared. This is to the power of 1. And we're multiplying it by x squared plus d squared to the power of 1/2. So basically here we have x squared plus d squared to the power of 1 plus 1/2, because that is how you add exponents here, which gives us 3/2. I know this is looking crazy. This is a lot of the stuff I forgot in the first solution of the problem. So this is physics for you. So anyway, let's see what we can do here. D is a constant. We can pull that out. So we have this I, D. I'm just recopying the shit from the front. And then I have integral negative infinity, infinity. Inside I have dx, x squared plus d squared 3 over 2, boom. Now how do we solve this integral? Well, you can plug this into an integral calculator. Most of the time in these classes, in the first kind of year that you learn this, you may be taking calculus adjacent to a class like this, or you may have never taken calculus before. The test is not going to expect you to be able to solve this. So most of the time, if you look in the equation sheet, this will be there, this general integral. This is a general integral. This, maybe they replace this d for an a, b, c, d, whatever. X is here, x is here. This is the variable of integration. You have this whole thing here, x squared plus d squared. D could be changed for any variable, right? And any letter, it's just a constant, right? It's just there, not changing. But x is changing is the variable. And this whole thing to the power of 3 over 2. Normally they give you this solution, which I will do right now because I do not want to x squared plus d squared, that to the power of 3 over 2, from negative infinity to infinity. Let's see, and we get a fantastic thing. This equals to 2 over d squared. Now we can simplify this a little bit more. I d 4 pi. Remember, this whole integral equals 2 over d squared. Now we can cancel some things. There's a d squared here and a d here that cancels, leaves 1. There's a 2 here that cancels with this 4 and leaves a 2. So we have mu naught I over 2 pi d. This is the magnitude of the magnetic field, a distance d from a wire. Notice that it is in terms of variables. I is a variable. So now if you have this equation for a magnetic field perpendicularly away from a wire at a point D, you can change I or plug in I, 1 amp, 2 amps, 15 amps, whatever, plug it in there. Mu naught is a constant. Normally it's given to you. It has specific units, whatever. You know what 2 is, you know what pi is. D is also a distance. So now you can change this variable. You can either increase D, decrease D, and you can see how that affects the magnetic field. So a little bit of kerfluffle here. This is how you use the Biot-Savart law to calculate a magnetic field a distance away from a wire. This law works for any object with a current. So the object could be a bit different, and this entire setup here changes depending on what your object is. Also, in a test, normally you're not expected to solve the Biot-Savart law if you want to analyze a wire. Normally you do this in the homework, and then you know that this is equal to B wire. So this equation is normally in the equation sheet, and you just know this equation is for a wire. So if they give you 2 wires, you can add up this to find the magnetic field between 2 wires, 3 wires, 4 wires, a thin wire. I don't know. Do with that what you wish. Thank you very much for watching. Peace out.